GAP 3.0s. Welcome to Mastering PCB Layouts for Optimal Electromagnetic Compatibility and Signal Integrity. To reduce EMI, always use solid ground planes, minimize loop areas, and route high-speed signals over continuous reference planes. Keep traces short and direct, separate analog and digital sections, and avoid running high-speed traces near sensitive analog lines. Decouple power at every IC with capacitors close to the pins, and use controlled impedance traces for critical signals. This series focuses on mixed signal designs under 100 megahertz with rise times above 1 nanosecond, and emphasizes best practices for 4-layer PCBs. Let's start with key EMC concepts. Low-frequency circuits can unintentionally emit high-frequency RF signals due to poor PCB design, like driving a 50 megahertz signal across a ground plane gap. Emissions traveling through air are radiated. Through cables, they're conducted. Circuits receiving these emissions are sensitive or immune, with susceptibility indicating how strongly a circuit is impacted by RF interference. Digital signals like a 10 megahertz square wave actually contain frequency components extending to gigahertz. The Fourier theorem explains this through sinusoidal harmonics, decreasing rapidly at higher frequencies. The bandwidth limit, determined by rise time, marks where these harmonics become negligible. For instance, a 1 nanosecond rise time has a bandwidth limit at 318 megahertz. On PCBs, the velocity of electromagnetic waves depends on the dielectric's permittivity. Wavelength, velocity divided by frequency, is crucial. At 10 gigahertz, the wavelength is approximately 14 millimeter. FR4, a common dielectric, yields a wave velocity around 141,000 meters per second. Wavelength, velocity divided by frequency, is crucial in PCB design. Trace lengths around a quarter wavelength effectively act as antennas. A significant EMC challenge arises when PCB traces unintentionally become antennas, especially if there's a split in the ground plane. Antenna reciprocity means structures good at transmitting also excel at receiving, causing both emissions and susceptibility issues. Intentionally designed antennas, such as Bluetooth antennas, often use this same principle deliberately. Understanding PCB structure is fundamental. A typical 4-layer board stacks signal, ground, power, then signal again. Internal layers usually handle power and ground, separated by dielectric materials like FR4. The outer layers carry signal traces, with core thickness typically larger than prepreg layers, influencing EMC performance. Common PCB geometries include microstrips, traces over a ground plane, and strip lines, traces between two planes. Trace dimensions and dielectric properties directly affect impedance, critical for EMC management. Consider this mixed signal system: sensor feeding amplifiers, ADCs, and a microcontroller. Rapid switching transients from digital signals and references typically create noise. Good EMC practices include continuous ground planes, proper decoupling capacitor placement, minimizing overshoot, and isolating sensitive analog signals. We conducted experiments comparing layout techniques' impact on analog performance, RF emissions, and susceptibility. Another experiment series analyzed digital communications, examining trace spacing, grounding, and via placement effects on noise. Measurements utilize high-frequency oscilloscopes, RF sniffer probes, amplifiers, and spectrum analyzers to capture near-field emissions. For compliance, far-field emissions would typically be tested in an anechoic chamber, though that's beyond today's scope. Today we covered foundational EMC concepts, PCB design methods, and measurement approaches. Let's review key points briefly through some quiz questions. First, which generates higher frequency emissions? A 10 megahertz wave with 1 nanosecond rise time, or a 50 megahertz wave with a 5 nanosecond rise time? Correct. The 10 megahertz signal due to its shorter rise time. Gap 3s. Next, would a low-level analog signal typically emit RF or act as a receiver? Correct. It likely acts as an unintended receiver due to antenna reciprocity. Finally, wavelength calculations help identify potential antenna issues. A 100 megahertz frequency on FR4 has a wavelength of approximately 1414 millimeters, meaning a quarter wavelength antenna would be about 354 millimeters. Implementing these principles ensures your PCB designs achieve better EMC performance, reducing interference and susceptibility issues. Future videos will delve deeper into advanced EMC topics and specific testing methodologies. Thank you for joining today's EMC series. Until next time, happy designing.